One issue that you might encounter when doing your calculations will occur when we're dealing with very, very small numbers in the concentration terms. When you raise them to a fractional power, you could get an error if the calculated number is less than zero. Let's look at just a simple experiment here. If I have a concentration that's 1 times 10 to the minus 6, and I want to raise it to the zero point 0.8 power, Excel can calculate that quite easily. However, if I do the same thing, but it's going to be negative 1 times 10 to the minus 6, the calculated variable, when I raised it to the zero point 0.8 power, we get this error. And this can happen when we're dealing with very tiny numbers in the calculated concentration terms from our model. And one way we can avoid that is if this number should be calculated, even though it's very small, but calculated to be less than zero, we're going to put in a variable such that it takes care of that. For instance, if I have a number that's negative, I can use an if statement, and I can say that if this number should happen to be calculated to be less than zero, then I will say that it is a tiny number. We'll go 1e to the minus 10. Otherwise, I'll just leave that variable by itself. If it's not less than zero, then I'll use that number and close that. So in this case, where it saw a negative 1 times 10 to the minus 6, it calculated to be that. And instead of using this in my calculation, I'll just have it take that into consideration. It's not going to affect your analysis. It's just handling just one of the issues that Excel has with dealing with negative numbers raised to non-integer powers. So how would we do that in our equations? Let's take an example here, and going to look at our calculated concentrations using our formula. So we're going to look at sodium hydroxide, ethyl acetate, and sodium acetate concentrations. And what we'll do is this. If our calculated value using the equation is greater than zero, then I'll use that calculated value. Otherwise, if it's less than zero, I'll put in a small number in its place. And that way, I can always guarantee that that number will be non-negative. And I can do that for all the variables here and have it calculate it properly. This way you can avoid that particular type of error during the analysis. In some cases, we saw that the calculated concentration was less than zero, and therefore it gave an error in the analysis. So this will get you around that particular problem. Now, once that's been solved for the first 5 room temperature experiments, we then go ahead and use the coefficients for alpha and beta for the experimental runs done at lower temperatures. And here we're going to use the Arrhenius equation to solve for this. So in our particular case, we did a room temperature run and calculated its K. Then we determined for other 3 runs at lower temperatures, in this case 9.9, 15.8, and 19.41 degrees C, we determined the value of K using this the same analysis while holding the alpha and beta terms constant. Now we're going to use a linearized equation of the Arrhenius expression, where we're taught in our reaction engineering course that we would plot the natural log of the rate constant. In this case, we would use natural log of K. And on the x-axis, we're going to plot 1 over temperature. And in this case, we want to convert our temperature into Kelvin, so we add 273.15 to it. So I have my natural log of K and my 1 over T. And if we plotted that expression, we would see that our experimental data fall on a straight line, which is it to be expected. And I can determine the slope and the intercept of this line using that feature. We can look at the slope of a natural log K and 1 over T and determine what that slope is. And the intercept can be calculated in a similar fashion. Note that when you use the intercept function, you're going to have the values of y first, then a comma, then the values of x. So my slope is equal to the negative of the activation energy divided by r. So all I have to do is take the negative of that and multiply it by r, and I get my activation energy at 33,479 joules per gram mole. And my intercept is actually the natural log of my pre-exponential coefficient. So I got to raise that to the exp to that number to get my activation energy. And so we have our two terms for our rate constant K. Then we can look at, well, what if I wanted to use nonlinear regression? And what we'll do is we'll use these values as a starting point. So I'm going to copy that value for my pre-exponential factor, and I'm just going to paste its value here. My activation energy, I'll copy that and paste it here, just the values. And so this will be our starting point. And now we'll use these numbers to calculate our model value of K. So we'll use the pre-exponential factor calculated by nonlinear regression, and then we'll multiply it by the exponential of the negative activation energy divided by the ideal gas constant R, divide that by the temperature in Kelvin. So here's my experimental value of K, and this is my model value of K. And I can use the solver routine to minimize the sum of the square of the errors. So my error squared is just the difference between the experimental and the model, and I'll square that and do that for all the other terms. And the sum of the square of the errors will be taken as these four values. Now I'm going to use solver. So I'm going to go to data and the solver analysis. And what I'm going to try to do is minimize the objective function, which is the sum of the square of my errors, by changing my variables A0 and activation energy. And going to hit solve and allow that to run its course and click OK. So nonlinear regression, we calculate slightly different numbers than what we had from linear regression. And if we looked at the plot of the Arrhenius equation, values of K, as a function of temperature, we see that both of those numbers, or both of the analysis, predicted the data quite well. The nonlinear fit is the solid curve, and the linear fit is the dashed curve. And so even though we had differences between the activation energy with nonlinear regression versus linear regression, and the the pre-exponential factor are significantly different. When you plot them against the experimental data, you see that one does not really have a benefit over the other. So you can be quite confident that either of these sets for activation energy and pre-exponential factor will do quite well. So this is how you would model the rate constant at different temperatures to get the best fit for the two parameters that are used in that model.